So in this lecture, we're going to talk about the observability Gramian and how you interpret it to understand how easy it is to estimate the initial condition of your system given a sequence of measurements and control inputs in some system model. Now, after we look at the observability Gramian, we'll shift gears to talk about Fisher information, which is an analog of the observability Gramian, but actually makes it a little bit more intuitive to understand the limits of your ability to estimate the initial condition of some system. So let's start out with writing out the observability Gramian as we've derived in previous lectures. The observability Gramian can be written as the observability matrix transposed times itself. And that comes from, remember, from our previous lecture, the second derivative, or the Hessian, of the output energy, which was the measurements transposed times themselves. So we take the Hessian of that relative to the initial condition. Now remember what that looks like in terms of a graphical shape. We have the initial condition on the x-axis, and the output energy is going to be quadratic with respect to that. And so it's going to have a general shape like this. So this here is the output energy, which is, we have written it out in discrete time as the sum of the measurements transpose times themselves. And the observability Gramian is really looking at the curvature of that quadratic shape. So what the observability Gramian really tells us is how the initial condition influences the outputs. But really what we might be interested in understanding is how the outputs can tell us about the initial condition. So we want actually the reverse of that. And intuitively, and indeed mathematically, the way you can do that is look at the inverse of the observability Gramian. So nearly all of the interpretations of the observability Gramian that we'll do actually come back to trying to understand how feasible it is to invert the observability Gramian and what the values are when you do that. So in order to estimate the initial condition given a sequence of measurements and control inputs and some system model, your observability Gramian needs to be full rank. Otherwise, you can't take the inverse. So let's write that out. So if your observability Gramian is full rank, then your initial condition is observable given the measurements and control inputs that you have over some time sequence. But we'd like to do a little bit better than just saying whether or not it's possible. We'd like to know how feasible is it really. So we'd want to understand, we'd want to quantify the challenge of actually inverting that observability Gramian. So we can use two different quantitative metrics that are commonly used to assess that. The first one is we can look at 1 over the smallest eigenvalue associated with our observability Gramian. So the smallest eigenvalue of our observability Gramian. That's going to determine how mathematically well posed that inverse is going to be. So we'll call this here lambda. The second metric is just a relative one. You may have a matrix that has some very large and some very small eigenvalues, and it's really the relative value that often matters. So another common metric is to look at the maximum eigenvalue divided by the minimum eigenvalue. And this is often called the condition number, which I'll abbreviate as CN here. Now, what happens if your system is not fully observable, or if there are some states that are very poorly observable? We'd like to understand a little better about which states are observable, or maybe which states are the most observable out of all the states that you have available. So again, you can use the eigenvalues and eigenvectors of the observability Gramian to understand that. It's most intuitive if you think about things graphically for a two-dimensional system where you could plot for the two states, state 1 and state 2, the eigenvalues and eigenvectors. So we can draw the combination of those where the vector gives you the direction, and the eigenvalue gives you the length of that vector. So maybe for one of your eigenvectors, it looks like this one here, where it's nice and long, and the other one perhaps is a really short little vector there. Really, these are associated with their opposites as well, and so what your observability Gramian tells you is the overall shape of this ellipse that tells you kind of the observable space for your system. So something like this example here would tell you that this state, or this combination of states rather, with the long eigenvector is the most observable combination, whereas the direction that is much shorter is less observable. So for this hypothetical system with just two states, what it tells us is that the combination of those two states is quite observable, but it is a little bit difficult to distinguish between them, given that one of these eigenvectors is quite small and the other one is quite large. Now, the observability, the eigenvectors and eigenvalues of the observability Gramian are a little bit difficult to interpret because they do only tell you about state combinations. It would really be much more convenient if we could understand how each individual state, how its observability was defined by the Gramian. There's also one other major limitation of the observability Gramian is it doesn't tell you how you should include the effects of either sensor noise or process noise. So to answer both of those questions, that is the effects of noise and how you should interpret individual states as observability, we can take a slightly different approach that has a lot of parallels. And that's where we transition to Fisher information. And so I'm going to draw this in parallel with our observability Gramian. I'll step over to the other side now. So with Fisher information, we can write out a very similar equation that you'll see some very strong parallels. So the Fisher information matrix is defined as negative the expectation of the second derivative, or Hessian, again, with respect to our initial condition. But now, instead of looking at the output energy, we look at the log likelihood function of our measurements given our initial condition. So let's talk a little bit about what this means intuitively. We're not going to derive this equation or make calculations using it, but it is important to understand how it's related to our derivation of the observability Gramian. That will give you some intuition. So again, we're doing something very similar. We're calculating the second derivative, or Hessian, to look at the curvature of some function. In this case, the curvature that we're looking at is of the log likelihood function. Now, if you looked at the log likelihood function for your system relative to some initial condition, it's going to have a very similar shape, except it's going to be opposite. What this says is that there was a particular initial condition that led to the most likely scenario of getting the outputs that you got. And what we're interested in understanding with the Fisher information calculation is how quickly does that likelihood change when you shift your initial condition. If this curve is very sharp, that means that it's very well defined how your initial condition is related to your outputs. If the curve is very flat, that means that there's a wide variety of measurements that could be associated with your initial condition, or conversely, there's a wide variety of initial conditions that could have given rise to the measurements that you got. Now, note that in the Fisher information calculation, we're calculating negative the expectation. So the expectation is what handles the uncertainty in this system. So here we are, remember, considering what are the effects of sensor and process noise. How do those contribute to the overall observability of our system, the overall ability to estimate the initial condition? So the expectation is necessary to handle that uncertainty. The negative there, that one's pretty intuitive. For the observability Gramian, we had a parabola that you see right here, whereas for the Fisher information, we have the inverse. And so in order for those two values to match, we need those curvatures for the Fisher information to be multiplied by negative. So again, we're not going to go through the derivation, but if you did not have any process noise, and if your measurement noise was given by the identity, then your Fisher information matrix is actually going to be equal to the observability Gramian. It's going to be equal to O transpose O. If you did not have any process noise, but you do have some sensor noise, so you have R being some matrix, typically diagonal, then your Fisher information matrix will come out to O transpose R inverse O. Finally, if both Q and R are not equal to 0, then your Fisher information matrix is again going to have a very similar shape. But now I've made one small change, which is I've added this tilde above the R to indicate that that R is not just your sensor covariance. It's going to be a function, that R tilde is going to be a function of R, Q, and your observability matrix. It's going to be a little bit gnarly to calculate, and we're not going to go through the derivation or form of that in this lecture today. Okay, so what does the Fisher information matrix allow us to do? Well, the reason it's so convenient is because we can use the Cramer-Rao inequality to better understand the implications on the observability of our initial condition. Sorry, this should say the Cramer-Rao inequality. The Cramer-Rao inequality says that the error covariance matrix, in this case for our initial condition, so I'll draw a little 0 there just to indicate that, must be bigger than or equal to the inverse of the Fisher information matrix. What that's saying is, given some system, there is a mathematical limit on how small that error covariance could be for your initial condition. And that limit is set by the inverse of the Fisher information matrix. So if you think of the Fisher information matrix, and you look at the inverse, then if you look at the diagonal elements of that matrix, those are going to tell you the lower bound on the error covariance for your initial conditions estimate for each individual state. So that tells you how well you could reconstruct that initial condition given your measurements in your system model and so forth. One challenge you might encounter is, well, what happens if F is not full rank? Then you wouldn't be able to apply this tool without any kinds of modifications. So if F is not full rank, you can make one very simple little change to calculate this. Then you can say that your error covariance for the initial condition is going to be greater than or equal to your Fisher information matrix plus some epsilon times the identity inverse. That epsilon times the identity just guarantees that that matrix, that combination of F plus epsilon times the identity, it guarantees that that is going to be invertible. You will get an inverse. Now, if epsilon is small, which it should be in order for this to be mathematically accurate, then the diagonal elements corresponding to states that are not observable will have their error covariance bounds approach infinity, which is appropriate because those states were not observable, so it should not be possible to get any kind of reasonable bound on them. So this is a really intuitive way to understand the observability of individual states within some system.